All right, today we're diving into a topic that's pretty much invisible, but has a massive impact on our daily lives. We're talking about micromeritics, the surprisingly big science of really, really small things. So think about this for a second. Have you ever wondered how a simple pill just knows when to release its medicine inside your body, and how it does it at just the right speed? It kind of feels like magic, doesn't it? Well, as you probably guessed, it's not magic, it's science. The secret lies in the collective behavior of millions of microscopic particles, all packed together, each with its own unique size and shape, working in perfect harmony. To really get it, we need to shrink down and step into the world of micromeritics. This whole field is dedicated to these tiny particles. And when I say small, I mean really small. We're talking about micrometers. And a single micrometer is 1,000th of a millimeter. It's hard to even imagine. So, what is it? Simply put, micromeritalics is the science and technology of small particles. Think of any powder you can imagine, flour, coffee grounds, you name it. This is the science that gives us the tools to understand and, more importantly, control that unseen world. So, what do scientists actually look for when they study these things? You can think of it like a particle's own personal ID card. Every single particle has a unique profile, a set of key characteristics that totally define how it's going to behave. And this right here shows you just how complex it can get. You see, for a perfect sphere, you could just measure the diameter and be done. But real-world particles are irregular, kind of lumpy. So we have to consider their length and width for size, their overall form, and even their circularity for shape. These tiny details, they are everything. And here's a super important point. A powder isn't a collection of identical twins. Not at all. It's more like a huge crowd filled with particles of all different sizes. So we don't just measure one particle, we have to measure the entire range of sizes in a sample. And we call this the particle size distribution. Now, to make sense of this distribution, we use a few key benchmarks. First up is the D10. This value tells us the size that 10% of the particles are smaller than. So you can think of these as the finest, smallest particles in the entire mix. Next up, right in the middle, we have the D50. You might know this as the median. It's the exact halfway point. 50% of the particles are smaller than this size, and 50% are larger. It gives us a great snapshot of the central point for the whole group. And finally, you have the D90. This represents the biggest, coarsest particles in the batch. Understanding this full range, from the little D10s to the big D90s, is absolutely critical. Why? Because a narrow distribution usually means predictable performance, while a really wide one could lead to all sorts of inconsistent results. Okay, so we know what to measure, but how in the world do we actually do it? Let's take a quick tour of the really clever tools that scientists have come up with to peek into this microscopic world. We're going to check out 4 main techniques: the classic microscope, a sort of high-tech sifter, a method that cleverly uses gravity, and a brilliant device that uses electricity. First up is the old faithful, microscopy. It's the most straightforward method you can imagine. You put the sample under a lens, and you literally see and measure the particles you're looking at. It's direct, it's visual, and it's really the foundation of all particle analysis. Next is sieving. Just picture a stack of kitchen sifters, but for a science lab. Each sieve in the stack has a mesh with smaller and smaller holes. You shake the powder through the stack, and the particles get sorted by size. Simple, right? But incredibly effective. Now for a really clever method, sedimentation. It's all based on a simple principle we've all seen. When you mix particles in a liquid, the bigger, heavier ones fall to the bottom faster. By measuring that settling rate, scientists can precisely calculate the size of the particles. So smart. And finally, the Coulter counter. This thing is amazing. It pulls particles through a tiny little hole, one by one. And each time a particle passes through, it creates a tiny electrical blip. The bigger the particle, the bigger the blip. This lets scientists size thousands of particles per second with incredible accuracy. Okay, so we can measure these particles with unbelievable precision. But so what? Why does it all matter? Well, It matters because these basic properties determine the bigger, what we call derived properties, that have huge real-world consequences, like how a powder packs together or how it flows. Let's start with density. First, there's what's called particle density. This is the true density of the solid material itself, with no air or gaps included. Imagine the density of a solid block of gold. That's its particle density. But when you pour those particles into a container, they don't fit together perfectly, do they? There are always tiny gaps of air between them. The density of the entire powder, including all those air gaps, is what we call bulk density. And this diagram shows the difference perfectly. On the left, you've got your solid particle density. On the right, bulk density. It's the same amount of solid material, but the bulk density includes all that air. And trust me, this distinction is critical for everything from shipping costs to making sure a pill has the right dose. The particle's shape also completely changes how a powder flows. We can measure this with the angle of repose, which is just the angle of the little cone a powder makes when you pour it. Rough, irregular particles create more friction, so they form a steeper pile. Meanwhile, smooth, spherical particles flow easily, almost like water. So we've covered the what, the how, and the why. Let's get to the big payoff and see how controlling these tiny details leads to a massive, massive impact in the world of medicine. I mean, this is where it all comes together. Controlling particle size directly controls how a drug gets released and dissolves in your body. Smaller particles have more surface area, so they dissolve faster and get absorbed by the body quicker. It's also vital for physical stability, like keeping particles from clumping together in a liquid medicine, and for ensuring dose uniformity so that every single tablet has the exact same amount of active ingredient. So there you have it. From the coffee grounds in your kitchen to the medicine in your cabinet, the behavior of all these everyday products is dictated by the science of the small. The next time you encounter some kind of powder, what will you think about its hidden properties?